The electricity that we get out of the outlets in our homes and our commercial settings is a kind of electricity we call AC. That stands for alternating current. That means that the direction of the flow of electrons is oscillating. In the United States, the frequency of that oscillation is 60 times a second. It means that we're not actually ever getting an electron to go from a power plant all the way through the power lines and then through our televisions and then circuit back to the power plant. There's just, imagine a highway with a bunch of cars bumper to bumper, and they're all go forward a little bit and back a little bit and forward a little bit and back a little bit. And that oscillation, because everybody's moving forward, pushes everybody forward, then they move back. That means that way down the road, the cars are moving, and that flow, even though it's not a continuous flow, is still something that we can work with. And one of the neat things about alternating current is that there's an interplay between the voltage, which is how much electrical potential energy there is available. Voltage you can think of as the analog of height in a gravitational sense, and current, which is the amount of charge that is flowing. And a transformer is a device. You'll see these on power poles and at power stations just driving around that look like gray garbage cans. What they do is they swap between voltage and current. The power lines that take our electricity to us from power plants are at very high voltage and very low current. And the reason for that is it's a more efficient way to transmit that power. A high voltage and low current is the same amount of power as a low voltage and a high current, but there's less friction in the wire, and so you lose less energy along the way. But then in our homes, we want a lower voltage and a higher current to power our devices. And so a transformer does that transformation. And this is a transformer called Tesla Coil. It's plugged in, so it's plugged into 120 volts AC, and that's a relatively high current and a low voltage. And what this does is it changes it to a high voltage and a low current. So this is a transformer that goes from low voltage, high current to high voltage, low current. And when I do that and I activate it, exciting sparks going on there, the voltage is so high that electricity is able to conduct between the metal point of the Tesla coil and the metal tip of this light bulb through air, which is not a conductor. It's that very high voltage, that equivalent of a very large height in the electrical sense, that enables the charge to jump across that gap of air. Whereas if I just have 120 volts, I'm not going to get any current flowing across that gap. I'd have to actually have contact there. And so light bulb to light up, and because I've increased the voltage a lot, and power is voltage times current, power is a flow of energy, so it's conserved, so my total amount of power is the same. If I go from a low voltage and a high current, and current is what can kill you, to a high voltage and a low current, they just sort of trade places. The product of those two things remains the same. So when this is at a nice high voltage, the current is so low that I can, in fact, shock myself, which I particularly like doing, and it makes my fingers twitch. I much rather have it when a student is here to do it to me. But you can see that it's not harmful at all. Whereas if you had the same electrical energy in the form of low voltage and high current by accidentally touching the power outlet with a conductor, then you would have a great amount of current going through, which can be fatal.